This video is an introduction to integration. You should already know how to differentiate simple functions such as powers of x. Now, suppose dy by dx equals 2x. What we want to know is what curve has a dy by dx equals 2x. So what is the function y such that if you differentiate it, dy by dx is 2x. Well, from differentiation we know this, that if y equals x squared, dy by dx is 2x. However, because if you differentiate a constant you get 0, if I write y equals x squared plus 1, or y equals x squared minus 9, or add or take away any number from x squared, if I differentiate each of these, dy by dx is 2x for each one. So we can see an illustration of this if we look at this diagram here. Each of these small dashes represents a value of dy by dx. We can see when x is 0, we know that dy by dx is 2x. When x is 0, dy by dx is 0, and so we have a horizontal gradient, so that the gradient is horizontal. If x is positive, 2x is positive, and the gradient is positive. The larger x is, the steeper is the gradient. So if we go along here, we're increasing x, so we see we can increase the gradient. The other way, when x is negative, we have a negative slope for the gradient, and the gradient is getting steeper and steeper when we have large negative values. We notice that if dy by dx is 2x, then it does not depend on y. So the value of dy by dx at any point on when x is 0 is 0. Here, when at this point, any of these points here, whatever the value of x is, it's the same value of dy by dx for any value of y. So if we join these up, for instance, if I take one like that, on this curve here, dy by dx is 2x. And on this curve, and on this curve, and on this curve, and on this curve. And as we can see, there are infinitely many curves. Each one is equal to x squared plus or minus a constant value. So we have a whole family of curves. So if dy by dx is 2x, then y is x squared plus some constant. We'll call that constant c, and it could take any value, positive or negative. It's known as the arbitrary constant. C is the arbitrary constant. So if dy by dx is 2x, then this gives the curve y equals x squared plus c. This process is known as integration. So we then may ask, supposing dy by dx is x, what curve has a gradient x? Dy by dx is x. Well, if 2x goes to x squared, x would go to a half x squared. We can see if we differentiate a half x squared, that will give us 2 times a half x, or just x, plus this arbitrary constant, which I'm going to call c again. This c stands for any other number, and we generally can keep it at the same letter c. So integration is the reverse of differentiation. We see if, if y equals x squared, dy by dx is 2x. If we reverse that process, dy by dx is 2x, y equals x squared, then plus the arbitrary constant. So let's take some other powers of x. If y equals x cubed, dy by dx is 3x squared. This would mean that if y was a third x cubed, dy by dx would be x squared by dividing by 3. We can say if y equals x to the power of 4, dy by dx is 4x cubed. So dividing by 4, if y is a quarter x to the 4, dy by dx is x cubed. By putting these into a table, we can say x integrates to half x squared plus the constant, x squared integrates to a third x cubed, and x cubed integrates to a quarter x to the power of 4. Well, we can see a pattern here. As we can see that the index 3 increases to 4, and then we divide by this 4. 2 increases to 3, and we divide by the 3. This could be x to the power of 1, and that increases to 2, and we divide by 2. This also works if x is x to the power of 0. If we increase 0 to 1, we get x to the power of 1, which is just x, and dividing by 1 is just 1 over 1, which is x. So that's just x. X to the power of 0 is in fact 1, of course, and so 1 integrates to x plus c. We can say what the next one is. X to the power of 4 would integrate to 1 over 5 x to the power of 5 plus c by the same process. And we can generalize x to the power of n. We can say integrates to increase n to n plus 1 and divide by the n plus 1 plus c. And that gives us a formula for integrating powers of x. And it works for any value of n except n equal minus 1. If n is minus 1, we have minus 1 plus 1 in the denominator, 0, and you can't divide by 0. This is the reverse process of differentiation. If y equals x to the power of n, we know that dy by dx is n x to the power of n minus 1. Well, the reverse of that, if dy by dx is x to the n plus 1, instead of subtracting 1 from the index, we add it, and instead of multiplying by the n, we divide by n plus 1. It's reversed, and we add the arbitrary constant c. Now, just as differentiation works for any values of n, positive, negative, fractions, any real number, so does integration. And so if dy by dx is x to the power of a half, we can say y equals x to the power of a half plus 1, 3 over 2, divided by 3 over 2, which is 2/3 x to the 3 over 2 plus c. For negative values, if dy by dx is x to the power of minus 3, then y equals x to the power of minus 2, we added 1, divided by minus 2, which we would write as 1 over 2 to the x squared and negative plus c. Now if we multiply our function by a constant, say dy by dx is 5x squared. Just as in differentiation, this doesn't affect integration either, and y would be 5 times the integral of x squared, x increased 2 to 3, divide by 3, so that would be 5/3 x cubed plus c. If you're integrating just a constant, remember that the integral of 1 is x, so the integral of 5 is 5x, and 5x and 5 integrates to y equals 5x plus c. Always change functions into powers of x. So here I've got 1 over x root x. We'll write that as 1 over x times x to the half. And then using the indices rule, we can add the indices. X to the power of 1 times x to the power of a half is x to the 3 over 2. And that would be x to the minus 3 over 2. So that's a power of x. And therefore y equals x increase minus 3 over 2 to a half divided by minus a half. So that would be minus 2x to the minus a half, or writing back into surd form, minus 2 over the square root of x. If dy by dx is 6x squared, then y equals 6x cubed over 3, which is 2x cubed plus c. Now, there is a notation for this, the integral notation. Instead of saying, as well as saying dy by dx is 6x squared, we can, to integrate, we can say use this notation here, this symbol here, which is it's actually an elongated S, and sort of 18th century S, which stands for sum. In addition, you have this dx here, so those two together make the integration notation, and we have the function 6x squared between the two. So we have the integral of 6x squared dx, we would say, equals 2x cubed plus c. So our formula for integration becomes a x to the n dx equals a x to the n plus 1 over n plus 1 plus c. If we want to integrate the sum of two terms, 2x cubed minus x to the 3x to the minus 2, like that, then just like in differentiation, you integrate each term separately and add them. So that would be the integral of 2x cubed, which is 2x to the 4 over 4, minus 3 times x to the minus 1 over minus 1, which equals a half x to the power 4 plus 3 over x plus c. You may need to expand brackets if you want to, like here, if you want to integrate x plus 2 times x minus 3, expand the brackets, which would be x squared minus x minus 6 dx, and then we integrate each term. X squared is x cubed over 3 minus x squared over 2 minus 6x plus c. We may need to integrate a fraction where the denominator x squared here is a single term, and you can write that as 1 over x squared plus x cubed over x squared, and writing each term as a power of x, that would be the integral of x to the minus 2 plus x dx, which becomes x to the minus 1 over minus 1 plus x squared over 2, which is minus 1 over x plus x squared over 2 plus c. Well, that's the end of this video on Introduction to Integration. Now return to Study Smart, where you'll find a simple exercise where you can practice integrating functions.